What's coming off around here?
If you guys playing railroad anymore today, there's a landslide, a new cut.
Well, the idea with all of this is to summarize overall what all of the major players are involved in this latest project that I have. It starts with the Power Cab. The Power Cab gets its power from this power supply through this interconnect board, and it also has a communication path that allows other devices, like here the extra cab, to be able to communicate as well with this Power Cab internally to create the DCC signal controls that are produced on the output from this connector that goes to the track. And maybe I should have shown that, but anyway, here's the idea of what's happening right here in terms of control is that what's coming through this cable is both a cab bus protocol and power. And the power, of course, is this power supply right here, which is a two-terminal, what I call wall wart power supply. Two terminals meaning it doesn't have a ground, earth ground, okay? So that comes over to the NCE USB Interface board, and that has circuitry on it, which converts, pardon me, it converts the I/O on this 422, the RS422 power bus, it's the power bus, from USB. So it's from USB to this RJ11 connector to the power bus. This then of course goes back to the Arduino's USB connector, and that the Arduino, as I've explained earlier, is now capable of supporting a Bluetooth channel to a PC, a separate PC. That PC, of course, being the one running the JMRI. And this Arduino board is being powered with this power supply, which again is a two-pronged power supply, not grounded, and it's what I call a wall wart. So we have two different power supplies in the system. We have a Bluetooth connection, which is wireless. There's no concern about any ground loops because there's no ground coming from that. There's no ground coming from here, and there's no ground coming from here. So all these voltages are basically relative, all relative voltages on either side of the equation. And of course, as I've discussed in the previous episode, the NCE USB interface uses this little chip right here. I don't know if you can all see that, but it's right there. And that is a DC to DC converter chip, or what I call a regulator, voltage regulator chip. Might be the wrong term to use because it's actually converting the 13.8 volts coming from this power supply to 5 volts, which is used by all of the components that are on this interface board. Now, with this display, hopefully you get a very nice top level understanding of all of the major players that are involved in this project. And as I've described in the previous episode, there are some concerns and also some updates to all of this. And for instance, the big update, I think owing to a subscriber who asked questions, that would be you, Chris, that this DC to DC converter chip is actually not independent as far as grounds. It ties the grounds together. And in that it does that, both of these power supplies will then have whatever voltage that they're creating through this cable will be normalized to one another in that they will now have a common ground reference. So hopefully that doesn't cause any kind of current loops, which, we don't want to have like one supply pushing the other supply or vice versa. And, in electrical systems with dual supplies, that can happen, but I'm inclined to believe that it won't happen in this case because neither one of these have a ground probe. Neither one of these have a ground connection. They're just taking the AC signal from the wall socket and converting it to a voltage. And so if they're common ground, the voltages are all relative to one another. So hopefully that won't cause any problems. I hope this helps dispel any confusion that may have crept into my discussions about, in particular, this board, the NCE USB Interface board. The first and probably most important issue I want to experiment with is whether I can have a serial connection between any two USB devices. To do this, I came up with the following simple experiment I'm showing here. I have two Arduino Unos with their USB connectors joined together using a USB cable having two Type B male connectors. The Uno on the right-hand side is programmed to initially set up a serial port on its USB, pause to allow time for the other Uno to initialize, then transmit the character A repeatedly at half-second intervals. The Uno on the left is programmed to initially set up the serial on its USB, pause, then continuously check for input on its serial port, and if any input is detected, it will display input on the LCD display. The Uno on the right is supplying power to the other via the red and green wires. Power cannot be shared over the USB cable even though these two conductors in the USB cable are connected. This is because every Uno uses the USB supplied voltage as an input only. Looking at the Uno, this schematic explains why that is. The USB 5-volt signal is turned on only if the 9.3 volt signal coming from the power supply is not connected. In that case, if it's not connected, the comparator here is going to actually enable this MOSFET transistor switch and transfer the 5 volts from the USB through here to the board. The 5 volts is distributed then to all of the chips on the circuit board. However, if the 9 volt DC is connected, then this voltage is applied across this voltage divider, so you'll get about a 4 volt drop across this resistor, and the comparator is going to in fact turn this off. It will not be enabled. So now that it's disabled, the regulator is converting the 9.3 volts to 5 volts, and that's the supply. But it cannot send that 5 volts back through the MOSFET switch to the USB while the power supply is on because the switch is off. So that's just how they all work. All of the Unos and I guess all of the Arduinos work that way. None of them can supply a voltage back to the USB connector. Here's the Arduino Uno codes for the two Unos that I have down here. There's two. The one on the right is called I'm calling this the transmit Uno, and this one here I'm calling the receive Uno. As I've already explained, this one, when it receives any character from here, will display a message. So on this one, you see that the transmit USB application is what it's sending is every half second the letter A. And then over here on the receive Uno, it's looking for a character or any kind of input that may arrive on this USB serial interface. And if it sees anything at all in the input buffer, it's going to write that message, the input message plus whatever the string of characters is that it received, onto the LCD display. This LCD display it's a long runner 20 by 4 LCD display module, and I use the liquid crystal library to communicate with it. So if anyone wants more information on this, or for that matter anything else that I present, please leave a comment, ask your questions, because I always respond to any questions that may be asked. Now I'll plug the whole thing in to get this experiment underway and see if any serial data is received. So we'll get the power, you'll see the LCD light up. There's power, and the LCD lit up. So at this time, it is currently transmitting the letter A through the cable to here. However, nothing's being received. So no message has been displayed, and it demonstrates that two standard USB devices cannot exchange data over their USB ports without having a host controller. There is a variety of USB controllers, USB on the go, or OTG, I guess is the letters for that. But on the go would be a different kind of serial interface chip, and it would also have a different protocol stack programmed into its microcontroller. So these two are just standard, and they just simply can't do it. So I'll explain why this initial experiment failed and what we're going to do to fix that. To understand why the initial experiment failed, I researched the USB standard publication. The USB communication takes place over a 2-wire conductor, and similar to the RS-485 differential signal used by the cab bus, recall this signal pair that we looked at earlier, the two USB conductors in here carry a differential signal. This means that only one device can transmit at any moment, either this one or that one, but they can't simultaneously transmit, obviously. So because of the restriction on access to the USB conductor pair, the USB system will require a controller to orchestrate the bus activity. With the NCE system over here, the orchestration is done by the Power Cab, and that by repeatedly issuing a predefined set of addresses and releasing the 2-wire transmission across here long enough for a test to see if anything responded that was addressed. So we discussed that earlier, and so I don't have to go back over that, but that's the similarity between the two systems. The USB system manages its conductor pair by requiring a USB device called a host. The computers with USB ports use USB host software. The host is responsible to identify and initiate all communication to its attached device. The USB device is designated by the standard as a device, surprisingly, but the devices come of two types. There's a hub, and then there's, which is a bus expander, and then all the rest are called functions. The host detects when the device is attached by an interrupt. The host hardware on the interface has a pull-up resistor which keeps the two lines, the D plus and D minus, high. So whenever they differ because of an attached device, it creates an interrupt so that the USB host software can then go and ask the attached device, what kind of function are you? And in our case, it would discover that it's a serial COM type device. So my experiment, in order to work, must have a host device, a USB host device. Since the NCE USB interface board, the USB device type here is a serial COM function, I need to add a host function to the Arduino, this one that communicates with the PC via Bluetooth. Fortunately, I can do that with the Arduino host shield. Let me show you that. It came in this little box right here, and let's see, open that up. It was pretty nice because, and I'm pleased with that. It came with an anti-static bag, and let's see if we open that up. My dog's climbing on me. He likes the crinkle sound. Okay, here we have it. And you'll notice that it has a Type A USB connector on it. So we would use a normal, I just happened to change it out. We'd have use a normal Type A connector to communicate with that from the way the experiment will work is I'm going to repeat it again, only using this shield on the receive Arduino, so that I should be able to get the code necessary to make this work and be able to communicate then from this Arduino, which is transmitting a letter A, to this Arduino through this shield, which adds the host. It's the host shield. So I have a host function, and then be able to display the fact that there's communications coming in by adding that display message onto the LCD display right there. So I'll share my efforts with the host shield in my next video, and hopefully I'll have in that one JMR working via the Bluetooth, and that'll be the last part 5 of this curious adventure. So if any of this was informative or interesting to you, please consider leaving a like. And if you would like to follow along with my HO scale stuff, I recommend that you subscribe. And I want to thank you for your time with me on this latest adventure in model railroading. I look forward to the next one, and hopefully it will be a final one and it will be successful. I just heard that Dan Thorne, superintendent of the Lehigh Terminal Railroad, is out in the yard and he's having a discussion with one of the engineers. Let's listen in. Dan, I forgot to put a like in for this video.
Why, Tom, you ain't done for anything like that in 20 years.
Gee, Dan, I just forgot. It won't happen again.
Don't you let me see you around these yards? Go on, go on.
You know, Dan, he's gonna forget the light again. He's done it before.
He knows better than that. Why, I'd have to rule him off the road.
Wow, geez, I hope Tom never makes that mistake again. He's a valued engineer on the Terminal Railroad. It would be a shame to lose him.